Okay, we have spent some time in the past videos considering how we can use these basic trig identities to form substitutions as part of our trigonometric substitution technique to solve different kinds of integrals. And here we have one that's a little bit different. If this one was on a test, how would you go about solving this integral, where initially it might throw you, see it's already in a trig form. But if we look at it some more, we see that, well, down here we have a square root sign, and inside we have 2 minus the cosine squared of theta, or we have a constant minus a variable squared, and that sort of fits the pattern of the types of integrals that we've been working with that are amenable to this kind of technique. And in fact, if we look at these identities, we see obviously this one resembles this identity, where we have a constant minus a variable squared. So if we just put aside for the fact our concerns that this is already a trig function and just treat it like a variable and apply our technique, where will all this lead us? So let's see. We start off by saying, well, let the cosine of theta we'll call that not the sine of theta, we'll call it the sine of x. And let's see, because of this 2, we're going to call it the square root of 2 times the sine of x. And clearly, this here is now going to become 2 minus 2 times the sine squared of x. So we have 2 minus 2 sine squared of x. We can factor that 2 out, and we're going to have a square root of 2 left over. 1 minus the sine squared of x, that would be the cosine squared of x. So clearly, this part of the integral is just going to be the square root of 2 times the cosine of x. That's no big deal, really. But what about this side, or what's left up here? Now we take our differentials. This is minus the sine of theta. Let's take that negative sign over to this side. So we're going to have the sine of theta d theta will equal minus the square root of 2 times the cosine of x dx. And you see what's happened. When we make this substitution here, this very easily becomes this, no problem. And here the rest of the integral, that gets taken care of when we take our differential, so we get an expression for this. So initially, what appeared as a rather strange integral, our initial integral here, it was really just a setup for us to make this substitution. Everything else just falls into place. Incidentally, we forgot to mention, when first looking at any integral, you might want to check out, can it be solved with a u/du substitution? Well, let's see, if we called this u, let u equal 2 minus the cosine squared of theta, du would equal 2 times the sine of theta times the cosine of theta d theta. Obviously that won't work out then because we have a cosine of theta here, an extra term. So a u/du substitution would not work out for us, which is alright because it looks like our substitution technique is going to work out just fine. So here, this integral now becomes sine of theta d theta minus the square root of 2 times the cosine of x dx divided by this, the square root of 2 times the cosine of x. So this simply is just minus the integral of dx. Obviously is minus x. So now we want to get this expressed in terms of thetas as our original integral was. So we go back to our substitution. The sine of x, that will equal cosine of theta divided by the square root of 2. That's the sine of x. So x will equal the inverse sine of the cosine of theta divided by the square root of 2. So finally we can say with our original integral here of the sine of theta divided by the square root of 2 minus the cosine squared of theta d theta equals minus x, so that will be minus the inverse sine the cosine of theta divided by the square root of 2 plus an arbitrary constant of integration. Let's move this up here. Here is our original integral. We got x expressed in terms of theta. We have minus x here, so it's just going to be minus this expression. And there it is. Our answer as a double trig expression, if you will, because we're taking the inverse sine of another trig function. There's nothing wrong with doing that. And in fact, we may have suspected that our answer might involve some sort of double trig expression because our original integral was in trig form. So that really wasn't too difficult. We've got some time left over here. Let's consider this. Let's go back to this identity. We didn't have to write it like this, of course. We could have written it as the sine squared of theta equals 1 minus cosine squared of theta. Perfectly valid, obviously. So what would happen if we had our original problem here, sine of theta divided by the square root of 2 minus the cosine squared of theta, and we convinced ourselves that u du substitution wasn't going to work. We said, well, here we have a variable minus a constant squared, just like this identity here, same general form. So let's use this identity here to form a substitution to try to solve the integral. So in this case, we would say, well, that this variable, which in this case is the cosine of theta, equal, call it the cosine of x, again times the square root of 2. Now, what is inside here of the square root, that's going to equal the square root of 2 just times the sine of x. And we use our new substitution, and taking differentials, we would say minus sine of theta d theta will equal minus the square root of 2 times the sine of x dx, and these go away. So when we use our new substitution, this is going to be this, the sine of theta d theta, that equals now the square root of 2 times the sine of x dx. So let's plug these in and see what we get this time. So we're going to have the integral of sine of theta d theta. That's the square root of 2 times the sine of x dx divided by this, which is this, the square root of 2 times the sine of x. So here, this is just going to equal the integral of dx. That's x, obviously. Now, what does x equal? Now we go to here and we say, well, the cosine of x, that was going to be equal to the cosine of theta divided by the square root of 2. So x, that's going to equal inverse cosine of the cosine of theta divided by the square root of 2. From our original substitution, the cosine of x is this, so x, that's going to be the inverse cosine of this. Well, so now we want to say that our original integral here, sine of theta divided by the square root of 2 minus cosine squared of theta d theta. Now we claim it's going to equal plus the inverse cosine of the cosine of theta divided by the square root of 2 plus an arbitrary constant. Before, cosine of theta divided by the square root of 2, inverse cosine of that, but before we got a different answer. We had minus the inverse sine of the cosine of theta divided by the square root of 2. Of course, if these are correct, if you take the differential of this, you should get this expression. Likewise here, I don't know if we'll have time to do that, but I feel confident that we do have the right answer, because if you remember how this goes along now, when you have inverse sine of u, and you take that differential, that will equal 1 over the square root 1 minus u squared du. And if you do it for the cosine, that equals 1 over the square root of 1 minus u squared du with a minus sign before it. So the integral of this was going to, you expect, would give us some sort of inverse sine function. That same kind of integral here, you expect would give us some sort of inverse cosine function, only with a minus sign before it. So you would expect then that we could get, in one case, an inverse sine, in another case, an inverse cosine of the same function, only they are, one has a negative sign and one has a positive sign. So either answer is correct, and again, it was just a matter of asking ourselves what general form is the integral in, and which identity do we want to apply to make our substitution. Okay, that's it. Hope it was worthwhile, and come back and join us for some more videos, and we'll try and solve some more problems together.